702 and Cape Talk.
The Naked Scientist.
Good morning to you, Chris.
Good morning.
We're starting off with a story from the world of science involving two monkeys that have been cloned.
Yeah, this made enormous headlines this week around the world when the journal Cell published a paper showing two baby monkeys in China. One is a little bit older than the other, but they are the first primates to be cloned. Now, if you cast your mind back about 20 years or so, you may remember the creation of Dolly the sheep. Dolly was cloned by taking an egg cell from a sheep, removing the DNA from that egg, then taking a skin cell from another adult sheep, getting the DNA out of that skin adult cell and putting it into the egg, where the chemicals in the egg cell then booted up the software, if you like, in the genetic information, and it led to the creation of a sheep genetically identical to that adult cell, which was Dolly the sheep. And there's the joke that's going round is that Dolly was called Dolly because the clone was made from an udder cell, and so she was named in honour of Dolly Parton. And when Dolly Parton heard about this, she said, "No publicity is bad publicity." Now, the thing is that the technology that created Dolly the sheep has not subsequently been able to be transferred to primates. It's been successful with cows, it's been successful with pigs, it's been successful with cats and dogs, but not primates. And so the big news this week was that these scientists in China had succeeded where others had failed, used a similar approach and produced these two monkeys. They're rhesus macaques. And because they're non-human primates, they have very similar egg physiology to humans, which argues that actually you could potentially go down this pathway for humans. But we should emphasise no one at this stage is saying they're cloning humans. They're interested in doing this to try to understand more about the embryology of how humans form, how our systems form, and if you can make tribes of genetically identical monkeys, it means you can study certain diseases much better. There are some subtle differences between what was done with Dolly and with these monkeys. For instance, they actually used fetal cells' DNA as the origin of the DNA rather than adult cells, and the process is still extremely inefficient. It took 79 embryo attempts before they actually got just these two monkeys, so we're a long way from making this de rigueur at the moment. But it's an important story because it's another milestone in our understanding of how cells, embryos and DNA all work together.
David, in Hout Bay, what is your question?
Hello, Chris. Can you answer this simple question? What causes night cramps?
Okay, well, when we have a cramp, what's going on is that the muscle has activated itself inappropriately. Supplying your muscles are motor nerves, and they come from the spinal cord, and each nerve cell branches in the muscle and supplies a squad of muscle fibres. Now, normally there are very good mechanisms in play that mean that when the muscle shortens, there's a feedback loop that goes back to the nerve that's supplying it and turns off the nerve that supplies the muscle. And when the muscle stretches too much, there's a feedback loop that goes in and enables the muscle to shrink a bit. And this keeps the muscle the right length. The muscle cells normally only respond to input from that motor nerve. Now, when we have a cramp, for some reason, and there's a range of reasons why this can happen, the muscle shortens and goes into a phase of contraction inappropriately. And not all the muscles, sometimes it's just some of the motor fibres in the muscle. The contractile elements shrink and contract, not all of them. It depends. Now, why this happens, there can be a range of reasons. One common reason is electrolytes. And what I mean by that are chemicals in your blood plasma and in your body, which when the levels are not quite right, they can trigger muscles to have cramps and spasms. Sodium, potassium, calcium, these things are all tied up in the electrical activity of the muscle, and if they're off kilter, they will cause muscles to have an increased likelihood of going into these spasms or inappropriate contractions. Why it happens at night, we don't know exactly, but some people are more prone to night cramps, and some people take quinine, the same thing we use to treat malaria or certain forms of malaria, because this does have some evidence that quinine can reduce the intensity or frequency of night cramps, although we don't actually really understand why. Although that family of drugs do block up the path of sodium in and out of cells, so it may be electrically stabilising the muscle and making it less likely to go into a cramp situation. Why this should happen at night, though, and happen more often at night, I don't know.
Paris, good morning.
Good morning. Morning, Chris. Just a question. Often I've watched the news and the anchor will talk to reports in the field. and they'll ask them a question, but the camera will be focused on the reporter, but you can hear that, or you can see that there's a delay in his earpiece. Why is there a delay between the earpiece and the actual video signal?
Hi there. Yeah, interesting question. Part of the reason for this is because of digital latency. And when we are sending data from a studio out to someone in the field, very often that has to go through a whole raft of processing, so computers and other digital equipment. Then it has to be transmitted to that person. Now, very often that involves going via a satellite. So if you're in the middle of nowhere, you need to go via satellite. Now, the satellites that are doing this bouncing of the signal from the Earth's surface to a satellite and back down to somewhere on the Earth, to do that, you have to use what's called a geostationary satellite, which are satellites which are staying in the same position relative to the Earth's surface all the time. The orbit that does that for a satellite is some 36,000 kilometres out in space. So your presenter in the studio has to send the pictures and the sound about 36,000 kilometres up into space and then back down 36,000 kilometres to the Earth's surface, then through another load of processing to present the information to the in-the-field presenter, who then has to engage with the question, process the information, generate an answer, and then the same journey has to be reversed to send the stuff back. And this all translates into this delay, which is why you see these people sort of nodding enthusiastically, even though the question finished about 30 seconds before, and then they begin to answer.
Jan, hello. Jan or Jan?
Hello?
Is it Jan?
Yeah, Jan from Parankua. Yes, Chris, thank you for taking my call. Temperature control of living beings and so on is extremely important. Now, we know that the hippo doesn't sweat. It has to go, when it warms up, it goes back into the water. Dogs don't sweat. They control airflow over their tongues. Now, my question to you is, a tortoise, how does it control its temperature? Because it has an outer shell, no sweat glands, and it has this very dry skin and scales on its neck and legs.
Okay, interesting question.
It is an interesting question. Just to return to the question of hippos, hippos do sweat. They make something called hipposudoric acid. This was published in the journal Science in about 2003. And what scientists did when they analysed this sweaty material coming off of hippos was they found it contains natural antioxidants. And it's a kind of pinky colour, and it works like a natural sunscreen. So the hippos secrete their own inbuilt sunscreen to stop their skin getting too fiercely damaged by the sun. But you're right that they do retreat into the water when they want to make sure that they don't overheat or make sure that their skin isn't too fiercely damaged by strong sunlight. So hippos do have a trick up their sleeves, but they do resort to water. You're quite right. Now, in terms of tortoises and things like that, remember that these are animals which are cold-blooded. Their body temperature is dictated by the environment. And there are lots of animals like this: lizards, snakes, other reptiles. Turtles are very similar. Now, what they do is to use the ambient temperature of the environment and their interaction with it in order to maintain as stable a body temperature as they can. A leatherback turtle actually has a clever trick. It has a very brown shell. It's put melanin, the same stuff that makes our skin brown, into its shell, and the turtle can control its temperature by turning itself into a solar panel. Goes out in the sun, rises to the sea surface, the brown colour absorbs energy from the sunlight and it will warm the turtle up. The turtle can then retreat underwater or get away from the sun to cool down again or go into cooler water at greater depth. Tortoises are going to do similar things. They use the coloration of their shells, which are dark to a certain extent, to soak up sunlight. If it gets too hot, then they retreat into a darker area and they radiate off some heat by staying in the shade, so they can control their body temperature in that way. And then overnight, because they don't want to get too cold, they'll go and find somewhere, a hole or something, or somewhere safe that they can retreat into and hunker down, often with other tortoises, because their combined body heat can keep them warm. And this means that they are able to operate to the maximum extent possible within the constraints of having a body temperature which is dictated by environmental temperature. Our big benefit as humans is that we are homeothermic, homeo meaning staying the same. We keep the same body temperature. We use our metabolism to do that. And this means we're much more active, and we can be active over greater extremes of temperature. And that gives us access to a much greater series of geographies over the Earth's surface, because we're not dictated to by the environment where we go, where we live, and when we do those things.
702 and Cape Talk.
The Naked Scientist.
Shireen, thanks so much for calling in today. What is your question?
You're welcome. Please may I ask Chris, when you sneeze, does your heart stop?
Hi, Shreen.
That's
No,
a crisp question.
the answer is thankfully no, because if your heart were to stop, then you would lose consciousness. So, no, your heart doesn't stop when you sneeze. Your heart rate may change a little bit because when you breathe in and out, there is something called sinus arrhythmia. And if you put your fingers on your wrist and feel your pulse, and then you take a deep breath in and then you breathe out very fast and hard, you will see that your pulse rate actually changes a little bit as you're doing that. And this is because as the pressure inside your chest changes, you affect the rate at which blood is returning to the heart. And if you change the rate at which blood returns to the heart, you actually also affect how much blood the heart has got to pump back out into your body. This is going to have an effect on your cardiac output and your mean arterial pressure. This will feed back on the heart to change its rate. So if you're returning a bit less blood to the heart, you pump a bit less blood more often to keep the pressure up, and vice versa. And that's why you will see your heart rate change with your breathing pattern. So when you take a deep breath to do a big sneeze, you may actually inadvertently change your heart rate just for a short while, but you certainly won't stop your heart.
Okay, let's take a question off social media as well, Chris. Here's one from Tulani. Tulani says, please ask Chris Eusebius, how deep is the ocean, Chris, and why is it so difficult to reach the bottom of the ocean?
It depends which ocean you're talking about, but if you're thinking about the Pacific Ocean, for example, down at the bottom of there, it goes down beyond 10 kilometres. And in fact, there are mountains down there taller than Mount Everest, which project from the ocean floor upwards, but because they're underwater, we can't see them. So the tallest mountain on Earth is actually in the Marianas Trench, or from the bottom of the Pacific Ocean. They're very difficult to access because as you descend underwater, the pressure of water above you puts enormous pressure on you. And the deeper you go, the greater that pressure is. And for every 10 metres you go underwater, that's the equivalent of 1 atmosphere of pressure at the surface. So when we stand here on the surface of the Earth, we're feeling air pressure at the rate of 1 atmosphere. That's the air above us up into space pushing down on you. You go 10 metres underwater, and that's the equivalent of a whole Earth's atmosphere again. You go another 10 metres underwater, now you're at 2 atmospheres. So you can see the pressure very quickly builds up. And if you are not in a vehicle, some kind of submarine which is adapted to take those kind of pressures, you can't access any great depth because your submarine will just implode or crush. So there are very specialist vehicles that can make it to these extreme depths, but they're a real feat of engineering. And it's also very hard to stay down there for a really long time because it's also very cold because the water's at about 4 degrees. So people do go down there. They don't go down there for long, and they don't go down there in great numbers. But someone I interviewed from the University of Aberdeen said he was rather depressed because he went and set up a mission to take actually this was a remote operated vehicle, so it didn't have a human in it, but he sent a vehicle to the bottom of one of the deepest oceans, one of the deepest parts of the ocean on Earth, got to the bottom, kilometres down, and the first thing he saw on the seabed when he turned his cameras on was a plastic raincoat and a plastic bag. And that's very sobering, isn't it, to think you get to one of the remote places on Earth, most remote places on Earth, and you find such a communal garden piece of rubbish that we've managed to litter down there.
I'll take another one from Twitter, Chris. This is obviously a Cape Townian. Boyd Tumela says, please ask Chris, why biologically do we go thirsty as human beings? And is it possible, at least over time, that our bodies may adapt to changing environmental conditions?
Yes, indeed. My sympathy to the people of Cape Town who are not very far away from Taps Off Day. The reason we get thirsty is because we have what are called insensible losses. As you go through the day, your bodily processes consume water. You're breathing and your breath is saturated with water. Your kidneys are filtering out rubbish from the blood and the body's waste products and the excess salts that you have, and they're throwing those things away. The only way they can throw them away is to flush them out with some involuntary water loss. So every day we have an obligatory need to take in our water to replace our insensible losses. Now, some animals are much better adapted to this, and if you live in very harsh environments like some of these rodents that live in the desert, they have extreme and profound abilities to concentrate their blood and concentrate their urine and not have to lose very much water. We have adapted to actually rely on a bit more water each day, 1.5 litres or so, and so as a result, we do have to replace that. We're not a desert rodent. You can train yourself to cope, and people who live in hotter places or train as an athlete can control their body temperature better and conserve water in different ways. But there are these insensible losses that you cannot get round, and so as a result, you do have to replace what you take in, or you will be dehydrating progressively, and that's dangerous.
Martin, you've been holding on. Go straight ahead with your question.
Hi, good day, Dr. Chris. I just want to find out, my question relates to cuteness, how we as humans perceive young animals, puppies or kittens, to be cute. Now, my question is, what would be the benefit of this emotion if it's a primal emotion? And what would be the benefit of that being between different species? Presumably, some of those animals that we find cute used to be our food, and probably some of them still are.
Martin, thanks, Martin. If I had an award, like maybe free water, I would have given it to you. I think that's the cutest question we've had in a couple of weeks.
I think that you've hit the nail on the head from an evolutionary point of view, because if we give us a tendency towards regarding baby things as vulnerable and needing nurturing and needing support, that's exactly what human babies need for us to keep them alive. If we didn't do that, then they would perish. I suspect that part of that innate tendency towards nurturing and protecting young and vulnerable transfers to other species. Why it should transfer to a dog or a cat as well as a human, I'm not sure, but I suspect it's all part of that same mechanism, that we have this instinctive sort of will to protect young and newborn and juvenile in order to ensure our own survival of our own species. And you're quite right that actually these very cute things could turn into things that could become our lunch, but equally, if we're not careful, they'll make us their lunch. So I think you could argue at a very early stage it's sort of tit for tat, isn't it?
Absolutely. Jevin Woodmead, welcome to the show. Put your question to Chris.
Yes, Dr. Chris. Just a question here. There's the wave-like and particle-like nature of light. And then from that is the Doppler effect, which has given us to believe that the universe is expanding because there's a red shift from the light that's coming from the stars and planets. And that is because the wavelength is stretched. And obviously, if it was contracting, it would be to the blue shift. Now, that I understand in terms of the wave-like nature of light. But how does that apply to the particle-like nature of light?
Yes, thank you for this question. It's a tricky one. Now, the reason that people decided that light must be waves is because when we do various experiments with light, it behaves just like water waves do. They can interfere with each other, and if you have two waves that arrive in sync together, so in other words, the same part of the wave is going up at the same time, they'll add together and make a bigger wave, so you get a bright spot. The opposite can happen, and light waves, which are opposite polarities, can cancel each other out. You get a dark spot. So everyone said, light is a wave. Then along comes Einstein, 1905, and says, well, actually, that doesn't fit all the time, because let's look at this thing called the photoelectric effect, where if we shine light on a surface that is capable of turning light waves into electricity, we can see that different colours of light, which are different wavelengths, some of them will produce electricity and some won't, or some will produce more electricity and some won't. Now, that doesn't really work unless you consider light to have packets of energy, which we're now calling photons, and that those packets arrive at a certain rate. So on the one hand, some of the experiments support the idea that light is a wave. Other experiments support the idea that light is a particle. And we have to live with the fact that we have to cope with both, because we can't explain how things work and the observations we make in terms of one entity alone. So sometimes we consider light in terms of unique packets of energy, photons, and other times we consider light to be a wave.
Chris, we're going to leave it there for this week. Thank you, as always, for sharing your knowledge with us. And I hope that you have a wonderful week ahead.
I will do my best. Thanks, everyone. Have a great week and see you next time. Bye-bye.